All right, yesterday we finished up talking about measuring things in a lab environment, right? And estimating one digit past whatever digit you're confident in. However, there's some terminology that gets thrown around every time you collect data, and sometimes people use it incorrectly, so I did want to clarify. And this is referring to accuracy versus precision. Accuracy means your data average is close to the correct value. And the way I always remember this is accuracy starts with an A and it's an average, right? So it's an easy thing to remember. Precision is different. Precision just means your data is all close together. It doesn't mean that the data is right. It just means all of your data is close together. The way I like to represent this is with a target. So you can imagine like an archery target. We could have 3 of them. Not the most beautiful targets, but you get the idea. Let's do an accurate one. And we know we want to hit the center of that target. That's the correct spot to hit. But maybe we're hitting here, 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 and here. The average is still going to be the center of the target, right? This is still accurate, but it's not very good archery. If we think about precision, it could be all off in one corner as a tight cluster of data, but it's not very close to the center of that target, right? And then we could have a situation where everything's lining up and this is both accurate and precise. Ideally, as scientists, we want to use tools so that we can make accurate measurements, and we want those tools to be calibrated so we can get both accurate and precise data, right? We want to get as close to the correct value as possible anytime we're collecting data. So we'd like to use standards as much as possible and then use the correct tool for the correct job. All right, so now what we've got to do is get into the nitty-gritty math, which I'm sure everybody loves, about significant figures. And there's a lot of rules with significant figures. How many of you have heard the term significant figures? So some of you may have seen this in science classes already. Significant figures refer to the digits in a number that you count as important, right? And the first rule that we have is that all non-zero numbers are significant. So for example, I'll give you this number. Got 423. How many significant digits does this number have? 3, right? It's got 3 non-zero numbers. It means it has 3 significant digits or 3 significant figures. All right. Second rule is all zeros that occur between non-zero numbers are also significant. So I'll show you an example. So let's say we have 103. This 0 is between 2 non-zero numbers, right? So we count that 0 as also being significant. So how many significant figures would this have? 3, right? We do want to count that middle 0. All right, the third one says that all zeros, which are to the right of a decimal and at the end of a number, are also significant. So I'll show you an example of this. It makes more sense in context. So if we look at this number, this 0 is to the right of a decimal and at the end of a number. Therefore, it is significant. And it's at the end. Whoop. Therefore, if we look at this, how many significant figures do we have? Not quite. If we look at these ones, we don't count any zeros on the far left-hand side. So don't count left zeros. All right, That means we have how many sig figs now? Just two, right? We've got the 1 and the 0. We don't count any of the leading zeros. They're not important. We only count any non-zero numbers and then any zeros to the right of the decimal at the end. Yep?
Just to show that it's less than 1, wouldn't you put the 0 before the decimal? Or just to clarify why you wouldn't do that?
Sorry, say that again?
Why you wouldn't count the decimal before, or the 0 before the decimal to show it's less than 1?
Any zeros that are on the far left-hand side, you just never count them as significant. Yeah, that's a good question, though. All right, so this one actually only has 2 significant digits. Like I said, you don't want to count any zeros to the left-hand side of a number or at the far left-hand side. However, if you've got a 0 at the far right-hand side, you only count it if there's a decimal point shown. We'll do some practice with these two. All right, the next rule says that all zeros left of a decimal and in a number greater than 10 are significant. So I'll show you what I mean by this. So if we look at this one, this 0 is left of a decimal. That means that this is rule 4. We do want to count that one, right? What about this 0 right here? Does that one count? So for example, the far right-hand 0, do we count that one? Well, let's look back up at rule 3, right? We said all zeros which are to the right of a decimal and at the end of a number are still significant, right? So this one's right of a decimal and at the end of a number. That means this one's also significant. And so I'll just say rule 3. All right, so if we count the number of significant figures for this number, how many will there be? 3. We want to count all the digits here. All right, so these do get a little bit tricky. I'll give you another example, though, just because chemistry is complicated. Let's do 1,000. What do you think? If we look at 1,000, we don't have a decimal. So do we count any zeros left of a non-existent decimal? No. So in this case, these ones don't count. Since there's no decimal. Therefore, this number, 1,000, technically only has one significant digit. Yep.
So don't assume that the decimal is not there. I mean, you don't write like if I have one item, you don't write 1.0.
Yeah, exactly.
So you don't assume.
I think I understand what you're asking. Let me show a counter example. So let's say a chemist writes down 1,000 with a decimal. Now how many digits are significant? 4, right? Because the decimal is shown, they're indicating a higher level of certainty. Does that make sense? If you don't show that decimal, you're not as certain. You're basically saying, I'm estimating the hundredths place now. So it is really important to include decimals if you're at all unclear. Yep.
So with that, you don't assume that there's a visible 0.
Yeah, you don't ever assume a decimal. You always have to look for that decimal. Great question. Okay, so let's do some examples because this is really tricky and it can make your head hurt after a while. But here's a list of examples, and I want you to help me determine the number of significant figures in here, and I want you to check with your neighbor and see if you agree. So I'll give you guys some time to work on this. All right, let's try this as a class, and I want you guys to help me out. For example 1, I think it's a lot easier than the other ones. How many sig figs are in example 1? 5, right? They're all non-zero, so we want to count all of them, so I'll just go ahead and say 5. All right, what about number 2? There's a decimal. Yep, we still count them all. They're all non-zero, right? So we'd say 4. All right, what about the next one? 5. Why do we count the zeros? Because they're in between non-zero numbers, right? So we would again say 5. All right, now the next one. It's a little bit trickier. 1. Why don't we count these zeros? Yeah, they're on the far left-hand side. You never count far left-hand zeros, right? So in this case, this would just be one significant digit. We don't want to count those green zeros, right? All right. On the opposite side, what if you've got zeros at the far right, but to the right of a decimal? Do you count those?
Yes.
Yeah, absolutely. So this one would have how many? 5. And then for the last one, how many significant digits? 6. In this case, just like before, you want to count this one because it's at the far right-hand side and to the right of a decimal. So this one would be 6. We also count the zeros between non-zero numbers. So this is a little bit tricky. It does require some practice. All right. I'm going to put down an important note. Significant digits are important for measured values. And like I said, we saw yesterday with measured values, it gives you a rough idea of your certainty with your measurement. So the number of significant figures you include is hugely important because it relays that certainty aspect. All right, there's a bunch of rules for doing math anytime you're doing math with measured values, so we got to jump into that next. So we'll do math with sig figs. Everybody's favorite topic, math. We'll do addition and subtraction. And the general rule for addition or subtraction is your results cannot be more precise than your least precise measurement. So I'll write that down. And then I'll show you a really simple way for determining the correct units to use, or correct numbers to use. So let's do an example. Let's say my first measured value is 23.112233, just a made up number. And then we've got 1.3324 as my next number that I'm going to add in. And then I've got 0.25. And so my goal is to add all of these numbers together. Which one's my least precise value? Yeah, the 0.25, right? So this one is only precise to the hundredths place. All right, so we can go ahead and plug this into our calculator. If you just plug it into your calculator, it's going to give you a big long number. It's going to be 24.69, I think 4633. And if we look at this, our final answer can only include up to the hundredths place. It can't go beyond that. So what I like to do is essentially do a hashed line down here. We know it can only be precise to that hundredths place, which means our final answer in this case is going to be 24.69. We don't include those trailing numbers. They're not significant. Does that make sense? Yep.
Do we round that, please, or do we just not?
That's a good point. So if you notice, the next number after the 9 was a 4. If you have a number less than 5, you keep that number as is. If the next number after it is 5 or greater, then you round up. So you do want to follow rounding rules. Does that make sense? Is anybody not familiar with rounding rules? All right. So let's do multiplication and division next. It's a little bit different. I'm going to keep this the same. All right, with multiplication and division, we follow a different set of rules. And for this one, your results cannot contain more sig figs than your number with the least sig figs, and I'll show you what that means. And I'm just going to abbreviate sig figs. So let's see this in an example. All right, so in this example, I've got 23.123.123. It's going to be my first number. And I'm going to multiply this by a second number, which is 1.3344. And we're going to assume these are both measured values, right? So we measured them with a yardstick or something like that. All right, for the first number, how many sig figs are there? 8, right? They're all non-zeros. And then over here, we've got our second number. How many sig figs? 5. All right, if we plug this into our calculator, we're going to get a big number out. So I'm going to say 30.855, what was it, 493, or 495.3315, big old number. So if we look at this one, what we need to do is chop it down so that it only has 5 significant digits, right? So if we do this, we would start at the first whole number. We'd say 1, 2, 3, 4, 5. So we wouldn't count any of these numbers. They're not going to be significant digits. Does that make sense? I think every year I teach this course, I'll put these questions on exams and students are like, oh great, I can just plug this in my calculator and then write it on my paper, and they forget about sig figs. I'm not testing your ability to use a calculator in this class. I want you to remember the sig fig rules. Does that make sense? Do you have a question?
Do we apply rounding to multiplication and division as well?
Yes, rounding applies for multiplication and division or addition and subtraction. In this case, the digit after that 5 was a 4, so we didn't worry about rounding up. You only round up if your following digit is a 5 or greater.
Okay, so we only pay attention to the one after. We don't go to like the 9 afterwards.
Yeah, so for example, if this digit immediately following was a 9, then we could round this 5 up to a 6. That would be all we'd do here. So you do want to watch out for rounding. All right, I'll show you guys some weird examples. This is how I remember sig figs. Oop. All right, the weird example I like using is 5 meters times 5 meters. It's going to be what? That's a little bit tricky. 5 times 5 is 25. However, we should include units. It would be 25 meters squared. However, how many sig figs do we have here? 1. All right, how many sig figs here? 1. How many sig figs should we have here? 1. Okay, so if we go ahead and we look at this, we'd say, all right, this first digit is significant. If we look after this, this is 5 or greater. So what would our correct answer be? It'd be 30 meters squared. So 5 or greater, round up. So this one does only have one significant figure, and we had to round up to get there. It kind of throws people when you're doing this originally. The reason we do this, though, is because we're estimating the ones place, right? Another way of thinking about this is it's saying, what's about 5 meters by about 5 meters? And we'd say it's about 30 meters, right? It's still that approximation, and we need to be careful with it. If we have a separate example, let's say it's 5.0 meters times 5.0 meters. Now all of a sudden, we've got 2 sig figs and 2 sig figs. And when we do our answer as 25 meters squared, this one also has 2 sig figs. So this one, we don't need to worry about rounding at all. This would be our correct answer. And it makes more sense, right? If you tell an engineer, I've got a board that's 5.0 meters, not about 5 meters, your final answer is going to be a lot more precise or accurate. Make sense? So in chemistry, 5 times 5 is sometimes 30. All right. Now what we've got to do is practice using these, and we're going to couple this into something called unit conversions, and this can be tricky. So we're going to spend a fair amount of time on unit conversions. And we'll go through some examples before I let you loose. All right, with unit conversions, the whole idea is we're not happy with the unit we have. We want to change it to a new unit. And I'll show you the easiest example. Let's say I have 2 dozen eggs. How many total eggs do we have? All right, so I don't want my final unit to be in dozen. I just want it to be in number of eggs. All right, what we first need to do is come up with a conversion. So does anybody know the relationship between dozens and items? 12, right? So 1 dozen equals 12 items. So this is our conversion factor. And this is important to have anytime you're doing a unit conversion, right? So I'll show you how I like doing it. Whenever I do these problems, I say, all right, I start out with what I know, which is I've got 2 dozen eggs. So start with what you know. And then what you need to do is multiply it by a conversion factor. And the way this works is we need to be sure to cancel out our units. So in this case, do we want dozens to be in our numerator on top, or do we want dozens to be on the bottom? On the bottom, right? If we put dozens on the bottom, then all of a sudden we can cancel dozen because it's both the numerator and denominator, and so it cancels out, right? So just using basic math rules. Okay, so we can do that, and then we can say, all right, there are 12 eggs in 1 dozen, right? So when we do this, we cancel out dozen. That gives us 24 eggs, right? Do we have to worry about sig figs here? What do you guys think?
No,
Why not?
because we have 2 digits, we already have 2 digits significant.
It's an interesting question, right? So when we look at 2 for the 2 dozen, a lot of students say, well, there's only 1 sig fig in there. Shouldn't our final answer only have 1 sig fig according to our multiplication rules? The answer is not quite as simple. If you go back to that note, I said you only use sig fig rules if you have a measured value. You don't measure eggs, you count eggs. So you don't follow sig fig rules with counted items. This is just basic math. Does that make sense? All right, conversely, let's do it the opposite direction. Let's say you've got 124 eggs, and we want to figure out how many dozen this is. All right, so I'll give you guys a minute to do this, but check with your neighbor and see if you're doing the math the same way that they are. All right, let's do this as a group. We're going to start out with what we know. We know we've got 124 eggs. We need to then multiply it by a conversion factor. Do we want dozen on the top or the bottom this time? Top. Okay, so we'll say dozen up here. And we know that for every 1 dozen, there must be 12 eggs. Right, so it's going to be 124 divided by 12. That's about 10.3 dozen. All right. The tricky thing is if you look up at our top example, you see how we had eggs on the top and dozen on the bottom? And then on our bottom example, we had dozen on the top and eggs on the bottom. It doesn't matter whether or not your conversion factor is right side up or upside down. The main thing to watch out for is that you need to make sure that your units cancel and that you're left with your desired units. So in both cases, we canceled the units we didn't want and we were left with our desired units. So that's just kind of a nice day-to-day example. All right, let's do some examples using scientific calculations. And for our first example, I've got 1.83 Yeah, sorry.
So do you always want to put the desired value on the top of that?
The desired unit should always be on the top.
Okay.
Yeah, the unit you want to cancel is going to be underneath. That way it cancels out. So in this example with 124 eggs, we wanted to cancel eggs. That means the egg unit should be on the bottom of your conversion factor.
Okay. Are we
Yep.
ever going to have more units, multiple units in one equation?
Yes, we'll do multiple unit conversions. We'll get there. So we'll start out with some easier ones. So let's say we have 183 kilograms, and I want to go to grams. Or sorry, 1.83 kilograms, and we want to figure out how many grams we have. So does anybody remember the unit conversion for kilograms to grams? It's 1,000, all right? So we've got kilograms on one side. We've got grams on the other side. Does the 1,000 go with the kilograms or the grams? Goes with the grams. And if you remember yesterday, I said it's important to remember which one's bigger. So in this case, kilograms is bigger than grams, right? That means the larger number goes with the smaller unit. Okay, so that's our conversion factor. Now let's try to do the math. All right, we've got 1.83 kilograms. We need to multiply it by a conversion factor. In this case, do we want kilograms on the top or the bottom? Bottom, because we want it to cancel out. Our desired units that we want are going to be grams. All right, so what number goes with the grams? 1,000, right? We saw that in our conversion. Doesn't matter if it's right side up or upside down, but it depends on the conversion you're trying to do, right? In this case, we want the 1,000 to be on the top. Okay, so now that we've done this, we can say kilograms are canceling out. We're left with grams as our desired unit. And our final answer, if we go ahead and write it out, would be 1,830 grams. However, it looks like we're measuring kilograms, right? You can't count kilograms, they're not items. So what should our final answer be? How many sig figs were in our measured value? Yeah, 3 sig figs, which means our final answer should also have 3 sig figs, which in this case it does. So you can write it as 1,830. That implies that this is 3 sig figs. That would be a correct answer. Let me change this to an or. Or we can write this in scientific notation. We can say this is 1.830 times what? Give you a hint. We're going to move that decimal point 3 spots over. Be 10 to the third. Grams. Whoops. Sorry. let me change this, 1.83 times 10 to the third grams. So let's go back and take a look at this. If we look at this one, this is 3 sig figs. We don't count this 0. And then this one also has 3 sig figs. So depending on how you write it, you might write it slightly differently. Both answers would be acceptable. Does that make sense? A little bit tricky. All right, let's do another one. This one's going to be harder. I'm going to share with you some personal information. I am 162 pounds on a good day. What do I weigh in grams? And I'll give you a hint. The conversion factor is 1 pound is equal to 454 grams. All right, let's try this as a class. Let's start out with what we know. We know the measured value, which in this case is 162 pounds. And we want to multiply it by a conversion factor. In this case, do we want pounds on the top or the bottom of our conversion factor? On the bottom. We want it to cancel out. All right, and then we want our final answer in grams, so I'll put that on top. So we've got a ratio of grams to pounds. So does the 454 go on the top or the bottom? On the top. It's paired with the grams here. And again, we can say, all right, we're canceling out our unwanted units, getting our desired units. If we go ahead and we plug this in, the answer I'm getting is 73548 grams. That's the number that's getting spit out of my calculator. Is it the correct answer? No, it's got too many sig figs, right? So if we go ahead and we adjust this for sig figs, how many sig figs should it have? 3. So what we can do is we can write this 2 different ways. We can say 73500 grams, because this has 3 sig figs. So like I said, we follow these rules. This one has 3 sig figs, 3 sig figs. What's another way of writing this? Scientific notation. So then we could say 7.35 times 10 to the what? So if we take this imaginary decimal, move it 4 spots over, we get 10 to the 4th grams. Either one of these is appropriate because they both have the same number of sig figs, and you can write it either way. It doesn't matter. All right, let's try a hard one. Let's do 124 kilograms to milligrams. So now we might have something a little bit more complicated, but let's write down our conversion factors first. So 1 kilogram equals how many grams? 1,000 grams. So that's one conversion factor. However, that's not getting us to milligrams. So then what we need to do is say, all right, 1 gram is equal to how many milligrams? 1,000. So in certain circumstances, you may actually have to use 2 conversion factors to get where you want to go, right? So if we do this, we can say really quickly, all right, we know what we have is 124 kilograms. We may need to do multiple conversions. All right, do we want kilograms to be on the top or the bottom now? On the bottom, we want it to cancel out. And our only relationship for kilograms is using the upper conversion factor, which means that grams must be on the top. And then what number goes where? 1,000 goes where? On top, right? It's paired with the grams. All right, that's getting us close. Now we've canceled out kilograms. We're left with grams. That's not our desired unit that we want. So what we can do is extend this on, right? We can say, all right, let's use a second conversion. All right, in our second conversion, do we want grams or milligrams on the top or bottom? What do you guys think? Grams should be on the bottom. We want to cancel out grams, right? So I'll put grams on the bottom. We'll put milligrams on the top. Now when we do this, we'll cancel out these grams units and be left with our desired unit of milligrams. All right, what number goes where? 1,000 goes on the top, right? Because it's coupled with the milligrams in our conversion factor. So we'd say, all right, 1,000 milligrams for every 1 gram. So what's the final answer, those of you with the calculator? 124 million. And our leftover units are milligrams. Again, we can double check our sig figs. This has 3 sig figs. What about our final answer here? Has 3, so it looks like we're in good shape. I can immediately box this and say this is a correct answer. Or what would be another way of writing this? 1.24, and then if we count the number of digits, we'd say 1, 2, 3, 4, 5, 6, 7, 8. You can move that decimal point 8 places over, so you could say 1.24 times 10 to the 8th milligrams. Either one is appropriate. All right, so these do take a little bit of work. The problem of the day has some of these unit conversions. I would recommend trying to get started on them sooner rather than later. That way, if you have questions, you can email me or ask for help.